Hello, everybody. This is Fundamentals Talk 412. What is it? What did I title this thing again? 5 things every Win32 developer should know. I'm Raymond Chen. I'm a software developer in the Windows User Experience team, which in normal language means explore and the things that come along with it. I hope all of you enjoyed this morning's keynote, those of you who managed to get up in time for it, and that you enjoyed whatever exciting things happened in Universal Studios yesterday. But now you get to sit in a chair and listen to me babble for an hour. When the PDC organizer asked me to give this talk, they said they wanted a 400-level talk, and they asked me what sort of topic I wanted to cover. And I chose the title, 5 Things Every Win32 Developer Should Know, since this is, as I look around at the software out there, there are often certain categories of mistakes that I see that I think, although perhaps not fatal to your application, certainly betray a lack of polish. And I was hoping through this talk perhaps to get 1 or 2 of those points through and help your software become a little cleaner in its user interaction and its overall performance. Don't mind the man with the camera, he's just here to annoy me. The 5 topics, so one of the little balancing acts I had to play here was that this was tagged as a 400-level talk, but if it's something that everyone should know, should it really be so advanced that only super propeller heads who go to 400-level talks should know it? So you may find that some of the topics I cover here perhaps don't deserve the 400-level classification, but I'm hoping that perhaps in combination, you'll feel some degree of satisfaction with having come here. The 5 topics I'm going to cover are sort of a mishmash. The first half is going to talk a little about performance. The first has the provocative title, What You Learned in School is Wrong. We'll see what that means. The second of the topics is playing friendly with others. This has to do with being mindful of how you're using resources and playing friendly. The second half is going to focus more on user interface issues. 3 categories of user interface issues that I see applications messing up with some frequency. The first is the confusing circumstances around the phrase large fonts. The second, review of the distinction between parent and owner windows. Terminology in this area tends to be sloppy even among people who are well versed in the topic, and this only serves to confuse matters further, and I hope that I can do a bit of clarification here for many of you that will be review. And then the third topic is the rather abstruse topic, but still relevant, of asynchronous input and synchronized input, and specifically how input becomes synchronized, perhaps even without your knowledge, and what this means for how you need to structure your user interface. But before we go into that, I'd like to pitch some other talks here at the PDC. Fundamentals 315, Powerware Applications, is taking place later in the day. It also falls into the category of playing friendly with others. And this is what I call a tax. This is a term that some of us use at Microsoft to describe things that software ought to do, but which often gets overlooked and which rarely gets considered in project planning. And therefore, from a management point of view, it's considered effort spent with no payback. Nevertheless, it is an important aspect to make sure that your application is polished and contributes positively to the overall Windows experience. I do wish to note that the location for this talk has changed, so if you're actually planning on going and looking it up in your mini guide, I believe it's moved to 411. The other talk that's happening later today is Fundamentals 421. Mayoni Stevens from the CLR team is going to talk about how memory management is done on the managed side, so she will be talking about the garbage collector. As for me, after this talk, I will be heading over to the Fundamentals Track Lounge and we'll be there the entire remainder of the day until the Ask the Experts begins at 6:30, at which point I will be at the Windows System Internals table. You are all free to stop by, say hi, pat my head, punch me. Well, maybe not punch me. And I will also be in the Fundamentals Track Lounge tomorrow until the end of the conference. Here are some talks that happened earlier that I would recommend that you have gone to. And if you don't have a time machine, you can check them out on the DVD. programming with concurrency, which talks about the difficulty of multi-threaded programming. And I captured this in the phrase, the dangers of trying too hard. And we'll see more along those lines in my first topic. And then the other talk that already happened is one on test automation and accessibility, which is another type of tax, which is important for automation, testing, and also for making your program available to users with physical disabilities, which is important if you intend to sell to, for example, the United States government. There are also community resources that are available, of course, all the time after the PDC. I'm sure these websites are up right now. There's the MSDN Development Center. There are various news groups. We recently, just in the past couple of days, launched a new forum category up on forums.microsoft.com covering Windows Vista programming. And I'm a moderator on one of them, the precise name of which I can't remember because I just learned about it recently. And of course, there's my website in which every day I post up a sometimes interesting, often boring, and usually controversial topic, essays on Win32 programming, which was sort of the inspiration for this talk in the first place. All right, so let's take a look at what you learned in school was wrong. The provocative title blurb I put in the talk description was on how your order n algorithm can beat an order log n algorithm. And in order to understand how this works, you have to go back to where is the first level of performance bottleneck. And nowadays, CPUs are fast enough for most things. This, of course, neglecting the very intensive calculation computations. But in a large category of software programming, performance is not necessarily gated by your CPU. And instead, it's the latency with which you can retrieve information. And I put a little parenthetical here. This may not be true, and you all know it isn't true, but it's true enough. The writer David Sedaris was often asked when in his stories, which he presents in an autobiographical way, whether the stories are true, and he always says that they're true enough. And I hope that this, while also not true, will be true enough. This is a chart that the precise numbers are not important, and you may see other copies of this chart elsewhere, and the numbers will vary. But the important thing to see here is the order of magnitude. If we decide that a CPU operation takes one time unit, whatever that is, then a memory access from a location that exists in the L1 cache is going to take about 1 to 2 time units. As you leave the L1 cache, hit the L2 cache, it gets a little slower. If you have to go out to main memory, it gets slower still. But then there's this huge gap between what happens when you stay on the motherboard and then when you have to retrieve data off the motherboard. And so, for example, the hard drive, you're up to 10 million units. And if you leave the machine by hitting the LAN or the WAN or by accessing slow media such as the floppy or the CD-ROM, then the numbers become absolutely abysmal. You're up in the billions. And so it's very important when you are looking at performance in the small scale to focus on not crossing that line. What does this mean? Well, one thing that if you attended Rico Mariani's talk yesterday is that pointers are expensive. In the context of the CLR, this means that object references are expensive in some sense. In the unmanaged side, one of the problems with pointers is that pointers point places. And obviously, if you needed a pointer to something, it'll probably be somewhere else. You need a pointer to something else, so it's not going to be a pointer to yourself. This means that the object that you're pointing to is probably not in the same cache line as the object that's that holds the pointer. If you allocated the memory off the heap, just called heap allocate or new or one of your normal memory allocation functions, the memory has a good chance not even of being on the same page. CPUs and operating systems are not very good at predicting this pattern of memory access. Sequential memory accesses to memory that are close to recently accessed pieces of memory, obviously are much more efficient. The CPU works on the cache level, a cache line level, so memory extremely close to the memory you've accessed recently is fast. And of course, on the page level, the operating system pulls in memory pages at a time, so that way memory that shares the same, on x86, for example, 4K block of memory, when you touch one, the rest of them come in, and the rest of them essentially come along free for the ride. And therefore, the motto is, it's the page faults, stupid. As we were, for example, in Windows XP, I worked on the new Start menu, and one of the things we looked at was why, when you hit the Start menu, there was often a pause of 1/4 of a second before the Start menu came up. And by profiling and looking very carefully at how we organize our data structures, we noticed that we were just taking a large number of page faults, trying to collect all the data, computing which 5 programs are the programs that we should promote on the left-hand side in your most frequently used programs list. And by adjusting the way we computed those values, organized our data structures, and caching things in a cleverer and perhaps more directed manner, we were able to reduce the latency of the Start menu significantly, so that now most of the time when you hit the Start menu, it just pops right up. The common language runtime, the people there are also very smart, and they already know this. They may have been the ones who clued me in on this. And the way the common language runtime memory allocator works is also very friendly to keeping memory that is used at the same time, or memory that is likely to be used at the same time, physically near each other in memory. As you know, the way the CLR allocates memory is that memory that is allocated at similar points in time occupies similar points in space. So here is how your order n algorithm can beat an order log n algorithm. One question is, how big is n? Sure, order n can beat order log n, but there are all those constants hidden inside the big O's. In a typical, for example, user interface type of application, if it's a list box, more than 10,000 items in a list box is unusable anyway, so there's no point in optimizing for the 20 million list box item case, because if you get to the point where you need to put 20 million items in a list box, you've already lost. I'm glad people laugh with agreement. Although you'd be surprised how many people ask me, how do I put 20 million items in a list box? So if n is bounded, then order log n is a constant, as is order n. It's all down to the constants now. In practice, certainly if you're going to keep all of your data in memory, and if you're a 32-bit program, n is not going to be more than 2 billion, because that's as many addresses as you have in the first place. So even if you don't think your values are bounded, they're still bounded. So from a theoretical standpoint, all these algorithms are constant. The question is now, how big is your constant? A simple array is the most friendly data structure from the standpoint of memory locality, because all the elements are stored directly next to each other. Once you touch one element, the neighbors reside in the same cache line. If your element's kind of large, it may occupy several cache lines, in which case its neighbors occupy the next cache line. Certainly its neighbors are going to occupy the same page. And if you're operating on an array, you're likely going to be doing linear scanning, in which case the operating system memory manager, once you pull in that page and you touch the first element to see if it's the one you're looking for, it's already paid for bringing in the remainder of the elements in that page, in which case you are taking advantage of the way the operating system predicts how you're going to use memory. If instead you had an array of pointers, certainly you could pull in the entire array of pointers quickly, but then once you dereference that pointer, you're going to go off to another page. And if these memory blocks were allocated off the heap, each one could in principle reside on a different page, resulting potentially a page fault for every single access, if, for example, this is your program coming out of minimization. As a result, data structures that keep data away from each other, certainly the frequently accessed data away from each other, are going to be less friendly and more wasteful. And the examples I give here are linked lists and binary trees. The worst case here is a linked list where you have a node and a pointer. And if you are walking this linked list to look for something, you touch the first element, you effectively pay for it. You check to see if it's the one you want. And if it's not, you then follow a pointer that takes you somewhere else, most likely on another page, which means you paid for an entire page of memory to be pulled in, and you only used 8 bytes out of it, which seems to be rather wasteful. As a result, even if you set up these very complicated data structures, splay trees, that sort of thing, you can, even though you have reduced the number of key comparisons, which is typically the computation that these the value that these theoretical analyses are focused on. Even though you've reduced the number of key comparisons, you've massively increased the number of page faults. And as we saw on the previous page, that a memory allocation, even coming from system memory, costs about 25 to 50 units, whereas a page fault is going to cost you in the millions. That's a very large penalty you're paying. And even if you can save one of those page faults, that can, if you save a page fault here, save a page fault there, at the end of the day, at the end of your operation, you can find that you've ended up saving yourself quite a bit of time. That's why I mentioned on the previous slide that, especially at program startup, that it's the page faults that dominate performance. One of the questions I get is, my app is slow to start up. What are the super secret evil tricks you guys at Microsoft are using to get your apps to start up faster? And the answer is, the super evil trick is to do less stuff. Because the stuff you don't do, it turns out I can do nothing really fast. So, for example, if you're starting up and you're initializing all these data structures, you arrange your data structures so that way you're allocating them off the heap, you're doing a whole bunch of stuff, you have the functions that you're calling at startup are scattered all through your binary. You have a 10-line function, it's 2K long, but it's the only function on that page that's used at startup. You wasted half of your disk I/O. You paid 4K of disk I/O to pull all of that in, and you're only using 2K of it. It might be that this function is 10 lines long, and in your startup code path, only 3 of those lines are executed, and the rest are a false branch. In which case, perhaps you paid 4K to page this function in, and you're really only using 1K of it. So you need to understand, when you are chasing your application startup performance, you need to understand where your time is being spent, not just in terms of where your EIP is when you're using typical profiling, where sampling profiling, or even what's it called, instrumented profiling. That will tell you what function you're in. But you also, the more important thing at startup is how many page faults did you take in order to execute all of those functions. And the linker, for example, has a facility where you can tell it what order you want your functions to be placed in the binary. So from your instrumentation, you can determine which are the functions that I actually use at program startup and group them together. So that way, instead of paging in half a meg of code and only using a quarter of it, you page in, oh great, I just made up a number and I have to do math. Half, quarter, 1/8 of a meg, which is 120 something. The point is that you spend all this I/O, you paid for it, use it. Don't spend money and throw it away. And at application startup, time is money. The last point here is pointing out that the people who wrote the base class library in the CLR know all of this, because Rico reminds them. And the data structures in there are very mindful of these considerations, that page faults really are what's controlling a large chunk of your performance. And I went backwards. If I was clever, I would have pointed out something on that slide. The next point is playing friendly with others. So one of the thought experiments that I often use is the what if 2 programs did this question. For example, somebody might ask me, I have a window and I want to make sure it's always on top no matter what. Is there a window style I can set so nobody ever covers this window? Well, what if 2 programs did this and then the user put one over the other? You now have 2 windows trying to occupy the same space, and somebody's going to lose. Some people decide to fix this problem by saying, well, I will run a timer. And every second, I will check to see if somebody's covering me. And if somebody is covering me, I'm going to push them out of the way. Now that works until 2 programs do this. And I think you can see what's happening. You have 2 programs, each of which, once a second, take turns as to who's in charge. We have seen this happen in programs that people pay for, where both of them decide that they should be the one and work really hard at it. And as a result, you sit there and you install both of these programs and you watch your screen. And you see that your icons change to the icon for one program, and then to the other one, and then to the first, and then back and forth. And it does this for about 15 seconds. Your machine is completely unusable. And then finally, one of them puts up a message box saying, hey, there's a mean guy around here. Okay, so remember, we're all in this together. The goal isn't for you to be cool. The goal is for the person who is running your program to be more productive. I'm going backwards again. One of the things that I also see is the use of polling to determine when the state of the system is changed, using polling as a mechanism for deciding what to do next. Polling works great when you're the only program running. But even if you're the only program running, I was wrong. It doesn't work great. For example, the power management people will tell you that if your program is polling, that's going to prevent the CPU from going to low power states. On a laptop, this means that the laptop is going to drain its battery faster. It's going to run hotter. Your end user will be more uncomfortable with his laptop or her laptop. Even on a desktop machine, the increased memory consumption is going to raise the temperature of the motherboard. It's going to turn on the fan. It's going to make things more annoying for the end user. Other consequences of polling: if you're doing things with the screen continuously, of course, that's going to prevent the monitor from powering down and going into a lower power state. It will keep the hard drive from spinning down. This includes, for example, just checking updating a value in the registry. Because the registry, at the end of the day, has to get saved out to disk. You touch a key in the registry idle flush code kicks in every so often and says, oh, that registry's dirty, I better save it in case something bad happens to the power. So if your program is even just updating a little, what time was it the last time I knew everything was A-OK? Even if you do that, you're going to prevent the hard drives from spinning down. And a much more obvious consequence of polling is that all the code and data that you use in your poll loop, if you poll something once a second, for example, all of those pages are going to be kept resident in memory because they're in your working set. This has a negative consequence on other applications, of course, because this is memory that they can't use for doing what the user is actually trying to do. The effect is magnified on terminal services, where you can have hundreds of users all logged in. Even if you say, well, I was very, very clever about how I set up my little polling loop. It only hits 1 page of code and 1 page of data. We'll say on an x86, that's 8K. 100 users, that's 800K. That's nearly a megabyte of memory that your application just took out of the system. Another important place where you need to play friendly with others is in the thread pool. I could use some waiting pool analogy, but I'm not going to. One of the flags that you can pass to the thread pool when you're scheduling a task is the execute long function flag. This is necessary for playing friendly with the thread pool, so that way the thread pool knows when it should prefer to spin up a new thread to service tasks that have been waiting. This is something that, although perhaps it keeps your program, your task is happy, it's running, but it's clogging up other tasks, and as a result, contributes to the overall sluggishness of your application. It's also important when using the thread pool to clean up behind yourself. If you are going to create windows, you should destroy them. If you initialize COM, make sure you uninitialize it. If you have unfinished business, make sure you take care of unfinished business before you give the thread back to the thread pool. For example, if you execute a program with shell execute, it has the opportunity to use DDE to launch the document into an existing copy of whatever program is responsible for it. And this means that it's going to create its own little window to continue the DDE conversation after the function is returned. If you then return immediately back to the thread pool, you have now effectively leaked a window onto the thread pool. Now, the problem with leaking a window onto the thread pool is that if the next task to execute on the thread pool, is not a UI task, but instead is some hardcore computational task, or is off touching very slow resources such as the network or the CD, you have created a hung thread. There's a thread that owns a window that should be pumping messages that is instead doing your computation or accessing the network. This results in, for example, if the user decides to change their screen resolution, everything just waits because the system is waiting for your program to acknowledge this resolution screen change. Send message callback is another example of unfinished business where you give the callback function, and that callback function is going to run eventually. And you need to make sure that that eventually has happened before you give the thread back, because the thread pool might decide that it has no more work for that thread and destroys it, and then the send message callback has no thread to complete the operation on, which can result in, for example, memory leaks if that callback was supposed to clean up something from that message. Remote desktop, another place you have to play friendly. Key point about remote desktop is that your video card suddenly becomes extremely slow, because, as you know, the desktop is being displayed on another machine. All video operations are now going over the network. This means bit-blitting large bitmaps onto the screen involves taking a large chunk of data and putting it on the network and putting it over there, which can result in long pauses and sluggishness. Animations, I'm sure that you've noticed that when you're running over a remote desktop, certainly over a slower connection, animations are very, very chunky. You want to, and again, in the terminal services case, you want to suppress unnecessary operations because they're going to consume CPU multiplied by 100 users, and you're going to have a lot of CPU going. So far I've been talking about things where you have to scale back your application, but here is a point where you need to take the opportunity to scale your application up. One of the problems when you're designing software is deciding what features you want to put in. But if you are focused on making sure that you run on whatever your baseline target machine is, this necessarily limits the type of features you're going to put in. Because if you put a feature in that perhaps your baseline machine can't handle, then anybody who runs your application on the baseline machine is going to see a very sluggish application and decide that your app bites. If, on the other hand, you decide to leave the feature out, then the people who have the high-end machines that can handle your feature are going to be disappointed that your application doesn't actually do anything and therefore bites. So in order to help your application set its defaults intelligently as to, for example, what features to enable, whether if you're a game, whether you want to use water reflection effects or not, if you are a productivity application, whether you want to do how aggressively you want to do background spell checking, or even if you want to make certain visual effects, if you want even to use certain types of visual effects in your application based on the quality of the video card. In Windows Vista, there's a new interface called iWinSat, which is a mechanism for your application to ask the operating system what the capabilities of the hardware are, and use this to determine how aggressively to push or scale back your features. This is the same mechanism that Windows itself uses to determine, for example, whether to turn on Arrow Glass, whether to turn on desktop composition, whether it should use high-definition decoding in playback of video imagery. The feature is not quite ready for prime time in the beta 1 disks that you got. A real version is in beta 2, but the purpose of this is to get the information into your head, plant the seed, make you realize that this is coming and that you can use it. The fact that Windows is providing this means that, for example, you don't have to go stare at large numbers of Intel documents and AMD documents to decide what's the best way to test for, or to what is the best mix of instructions to determine how computationally powerful it is. Oh, and there was that email address at the bottom, WinSatFB, is the WinSat feedback alias that you can send any additional questions and comments to on that, because I have only 2 slides on this topic. The metrics that WinSat covers: graphics capability. This is expressed in frames per second and is used by the composition desktop window manager to determine whether or not to turn on composition. The actual unit, I may as well just go through the others. The gaming capability is doing D3D type computations, determining what is how powerful the shader is, how powerful the pixel shaders are. System memory bandwidth is basically determining how fast chunks of memory can be block moved from one location to another. Processor throughput runs the CPU through a realistic computation sort of exercise. It exercises encryption, decryption, and compression, decompression to come up with a rough number of, it's called megabytes per second processed. So presumably this is in terms of how many bytes can be compressed. But of course, your program isn't necessarily doing this for compression, but I'll explain how this works in later. And then the last one is disk sequential read throughput, which is it goes out, hits the disk, and determines what the megabytes per second transfer rates are, and gives you advice on how large your buffer sizes for streaming should be, for example. The results that I gave you, these basic numbers, is just the top, the top level of the type of information WinSat can provide to you. You can actually dig deeper and ask for much more specific information, triangles per second, various shading capabilities and performance, to see, for example, if I need n,000 triangles per second, what is my effective frame rate going to be on the current video card that's installed? These values are computed on first boot, so that way there's always some set of numbers available for querying. If the user swaps out their video card, WinSat is going to go in and do another set of computations, so that way the values in the capabilities database are up to date with the new hardware. And you can, in your application, for example, in your application setup, query or in fact ask for new numbers to be computed to determine whether you want to turn various features on or off by default based on the hardware capabilities. The precise units in which these values are reported to you isn't all that important. They could just be in arbitrary X units, because you can use this information rather more in the sense of having, for example, a copy of your baseline machine and a copy of what you consider to be your high-end workstation machine, and query these metrics and see that, for example, oh, my baseline machine, if I ask it these questions, I get a number of 300, and my high-end machine gives me 900, and this machine in the middle gives me 500, and then I try my feature out and see that, well, it looks good on the 500 and the 900, but not so good on the 300. So I'll turn off this visual effect if the metric comes out less than, say, 400. And you, of course, can try to fine-tune it, swap in new video cards, collect a variety of data, and decide where your cutoff is going to be on when you want to promote a particular feature. So that's why I didn't memorize the precise units in which these were reported, because it turns out it's not important. Okay, let's move on to user interface issues. The first is the very confusing term large fonts. Large fonts is used to describe both the magnification of fonts in user interface elements as a result of going to the display control panel. As you see here, the display control panel, and you can choose large fonts or extra large fonts to cause the size of title bars, menus, icon captions, status bar, tooltips, those sorts of things to increase. However, this affects only those 5 or 6 fonts and the corresponding metrics. As you can see in this dialog box, for example, the window caption and the various other elements have gotten very large, but the text in the dialog is still at the old size. So this is one thing people say. Sometimes what people mean when they say large fonts. Another thing people mean when they say large fonts is what we are now calling high DPI. This is where you can go into the advanced section of the display control panel and specify what the mapping is between point and pixels. This is a system-wide configuration setting and affects the conversion between points or other physical dimensions and pixels, which is used most visibly in dialog boxes. So for example, if you have a dialog box element that is 8 DLU tall and you have a font that is, for example, 8 point tall, 8 point at 96 DPI comes out to, I have my cheat sheet, 11 pixels. The formula, of course, is point is 1/72 of an inch, so it's 8 point times 96, 8 point times 96 DPI over 72 point equals approximately 11 pixels. Therefore, if your dialog box has an element that's 8 DLU tall, it'll be 11 pixels tall. On the other hand, if the system is set to 192 DPI, then 8 point at 192 DPI, according to my little cheat sheet here, is 21 pixels by the same formula. And therefore, your element on the dialog box if you specify that it's 8 DLU tall, is going to be 21 pixels tall. So here is an example of, I just threw together a quick little wizard, and on the upper left is what this dialog box looks like when at sort of normal 96 DPI and no special settings. On the upper right is what happens when you turn on extra large fonts. And as you can see, the only thing that changed is the size of the caption bar, because the size of the font is specified in the dialog template, still in point, and since we didn't change the dot per inch setting, the relationship between point and pixels hasn't changed, and therefore the font still comes out at 11 pixels tall. On the other hand, the dialog in the lower left is set at, I believe I put this one at 96, 120 DPI, and so you see that well, maybe you can't see, that the text itself has become larger, that the dialog box is itself physically bigger, and that the bitmap space on the left-hand side has correspondingly grown, because in the dialog template, that bitmap space was specified in dialog units. And since we've increased the DPI, this changes the factor by which point changed to pixels, and the size of that bitmap area is specified in dialog units, which scale with the font, which is specified in point, and as a result, the space allotted to the graphic has gotten larger, but the graphics itself, I, on purpose, left the old graphic in. The samples on the lower right-hand side are another illustration of what happens when you switch from, in this case, I switched from 96 DPI to 120, is that fonts don't scale perfectly linearly. If you change the height of a font, if you make a font 50% taller, this doesn't mean that all the characters are going to be 50% wider. And here's an example of a checkbox that is an actual checkbox that I had to fix, where the checkbox looked fine at 96 DPI, but if you change the system DPI up to 120, the text is now truncated because the characters got wider faster than they got taller. So here's what you can do about at least the bitmap scaling problem. So as you see on the left, on the first example is the bitmap. If you just specify your control style as SS bitmap, that is not going to perform any scaling. Your bitmap will just go into the corner, and the dialog's gray background continues to show through. If, on the other hand, you set the SS real size control flag, this tells the static control that it should take the bitmap and stretch it to the size that the control was created at. And so you see that this particular bitmap with the computer and the floppy disks has gotten stretched, and it looks kind of chunky. The third example is if you use the SS center image flag, which tells it to take the bitmap and put it in the center of the static text field, or in the static control, and then to use the pixel in the upper left-hand corner of the bitmap to do the fill. So here I illustrate the various options you have available to you. One is to leave the bitmap at the same size, but of course that leaves ugly gray bars around it. There's the real size control, which stretches, but then you have this stretching artifact. And then you can use center image, which preserves the picture, but tends to fall apart at even higher DPI, where you have a giant green field with a tiny little picture in the middle. So how do you deal with high DPI? As I noted before, font metrics scale nonlinearly. As a result, you need to visually inspect your dialogues at all of the DPI settings, and we recommend that you take a look at your dialogues and DPI settings from 96 up to 192. These 96, 120, 144, and 192 are the recommended DPI settings that Windows Vista will provide to end users, and so the likelihood is that the DPI setting on the system is going to be one of these four. Your bitmaps, assuming you're running Win32 code, will have to be adjusted. It means that you may want to provide a set of 4 different bitmaps for your illustration, one to be used at each of these common DPI. And if the user has selected a DPI different from one of those 4, you can choose either to stretch or to center one of these static images into the size that the user has selected. Stretching down is better than stretching up. We've just determined this visually, that if you take a bitmap and you stretch it, make it larger than it originally was, you can see the artifacts of the stretching, and it doesn't look very pretty. If you take an image and shrink it down, so for example, if the user had set a DPI around 130, the recommended solution is to take the 144 image and stretch it down, because that gives the stretching code more pixels to work with and try it, so it can come up with a better looking image. And the last one is the fact that high DPI, as I say, is the new multi-mon. You may remember that multiple monitor support came out in 1998, and a lot of applications just sort of fell over. But the system tried its best it's like, well, if you keep everything on one monitor, everything works great, and you can take your chances if you move things off to another monitor. And today, the story with high DPI is roughly the same. Most applications look really great at high DPI. Most applications look great at 96 DPI. But if you go into the display control panel and crank it up to 96, things start to fall apart. You see applications with edit controls off positioned, controls don't line up, there's overpainting, all sorts of various visual artifacts that make your program look less polished. So here are examples of some high DPI devices that I shamelessly stole from another talk. On the left is a tiny little handheld Sony Vaio, 6 inches, 8 by 6. This one is 166 DPI, and these prices are, I went online and started shopping around. I'm not a very good haggler, so these are probably not the best prices you can get. So don't try to buy them from me. In the middle is a Toshiba tablet, which many of you may have. And on the far right is one of these fantastic trust fund baby super LCD panels, $8,000, 200 DPI display. Looks great in the store. But imagine how disappointed a user is going to be. They go out, they buy this fantastic monitor, and then they run your program, and your program just looks like a piece of junk. This is known as an unhappy customer. So what's Vista going to do about this? Well, the large font scheme, thankfully, is gone. So the phrase large fonts now means only one thing. We had to do a bit of negotiation with the accessibility team and make sure that all the scenarios that large fonts were being used for were taken care of by other means. The desktop window manager is going to, by default, emulate a 96 DPI machine, regardless of the actual DPI setting that you've selected in the display control panel. So if you just take your average old program and run it, and it asks, what's the screen DPI? The answer will be 96. It will then take whatever that program does and stretch its output to match the output that the user has selected. So if the user has selected 192 DPI, it's going to ask the program asks, What's the DPI? The desktop window manager says it's 96. The program does its thing. The desktop window manager then stretches it out to 192 DPI, so it's going to look really blocky. But all the elements, at least, won't have this horrible overlapping, mismatched, overpainting problem. So the recommendation, of course, is for your application not to be one of these lame applications that can't handle high DPI. If you call the function setProcessDPIAware, this tells the desktop window manager, hey, I went to Raymond's talk. I tested my app on high DPI. Don't do any of this funny, horrible stretching. I'll take care of it. As a result, you're essentially taking upon yourself the burden of testing your application at these higher DPI settings and making sure that all of your layouts and painting looks good. If you are the sort of person who uses the Windows Presentation Foundation, you're in luck because that already was designed with high DPI in mind, and the mechanisms that are used in that system are already DPI agnostic. So the theory is that you don't have to do anything to be able to take advantage of high DPI systems. The exception is for resources that are already specified in pixels, such as bitmaps and, to some extent, videos, in which case you still need to go through some degree of this type of calculation to make sure that they still fit in with your application's visual appearance. Still on the topic of looking good on Windows Vista, there's another talk right after this one, in that room over there, I believe it is. Building applications that look great in Windows Vista. This talk is going to go into the new common controls, including the task dialog, and on how to use Glass in your application. And Cheered is going to go into the philosophy of Arrow, so that way you understand what the new look is trying to accomplish. And then Jeff is going to give you advice on how you can incorporate this in your application so that your application fits in with the philosophy and the look of Windows Vista and therefore contributes to the seamless experience. The next topic, parent and owner windows, is going to be review for most of you, so I'm going to kind of hit the main points and just try to remind you of what things to watch out for. The parent-child relationship is one of containment. A child window resides within the client area of its parent. The ownership relationship is a relationship among top-level windows. If one window owns another, the two of them still maintain separate screen positions. They can overlap. They need not be constrained within each other. The owner relationship however, does ensure that the owner resides behind the owned window in the window Z order. So this is one way to make sure that one window always appears on top of another. Most of the window creation functions will take a parameter, a window handle parameter, that is often documented as the parent or owner window, depending. If you understand how the distinction between child windows and owned windows, you can determine, you can see that the depending is based on whether or not the window being created is a child window or not. If the window being created is a child window, then this hwind, owner or parent, is the parent because child windows have parents. If the window you're creating is a top-level window, then a window that you pass here is going to be the owner because top-level windows have owners. Most functions that put up UI in some degree or other is going to have an hwind parameter, which is almost always, I can't think of any examples right off the top of my head where it wouldn't be, the owner window. This leads into the next topic, which is, actually it's going to lead into topic 2 slides from now, so I will hold off. Parent-owner confusion, there's quite a bit of confusion that I'm sure is partly Microsoft's fault. The function called getParent returns the Windows parent if it's a child window, or its owner if it's a top-level window. So its name really should be getParent or owner. But it turns out this function got its name back in 1983, and it's kind of late to change it now. As a result, there's a new function that was added in around 2000 called getAncestor, which makes it clear what kind of a window you're getting. You say getAncestor GA root parent or GA root, which says, I want to take this window and walk through its parent chain until I find the top-level parent window. You can look in the documentation for the other flags. And I would recommend using getAncestor. Certainly, it's clearer what you're getting. And it makes it easier for people who stumble into your code to understand what type of window you're looking for. As I noted before, the documentation is often very casual about the distinction between parents and owners, because a lot of times the parameter is used both as a parent or an owner, depending on context. And sometimes it's just because people like to say parent, because I guess owner is a sort of more awkward word. But in reality, you need to, when speaking, and you can certainly call me on it whenever you see it, to be clear about the distinction between parents and owners. So here's an example of of a visual tree. We have an extremely bad drawing of Notepad with an edit control in it and a find dialog that's popped up with its own edit control and an OK button. And then there's some other simple window off to the side. And the diagram on the right is the window tree that you're all expecting to see. There's the desktop, which is sort of the implied parent, so to speak, of all top-level windows. And there's a find, and the find, of course, comes first because it's first in the Z order. Next comes Notepad, and next comes simple. And then under those are its child windows. In another set of bookkeeping, there is a sort of tree, except it's not really, but you can think of it as a tree of owner windows, where the members in this tree are the top-level windows in the window hierarchy, and that the sort of the elements closer to the root are elements that own other windows. So in this diagram, find is an owned window owned by Notepad, and therefore if you call getOwner on find, it's going, well, there's no function. If you call getParent on find, it's going to return Notepad. So one of the problems that I see often is when people play games with parenting and reparenting. So as I noted before, only top-level windows can be owners. Ownership is a relationship among top-level windows. If you pass a child window as an owner, for example, if you are a property sheet page and you pass your own window handle as the owner handle for a call to message box, the window manager is going to walk the window hierarchy from the window you pass as the owner back to the root of back to the root of that parent hierarchy, looking for the top-level unowned window, and use that as the owner instead. As a result, if you are playing games with reparenting, you can find yourself in a state where you've taken a window, it has popped up a dialog box or something that it owns, then you take this window and you shove it into another window tree. This owned window it didn't travel with it, because this owned window, its owner is not you. Its owner is your root parent. Sometimes I see this, you do a little, some applications have this little undock type functionality. You take a window, you undock it, and the dialog, and if you do it while it has a dialog up, the dialog just sort of floats there and things get very confused. There's a way you can update the owner of a window. There is no setWindowOwner function, but it turns out that there is. It's just not called setWindowOwner because apparently we don't like making things easy. So I have given you the setWindowOwner function here in this slide. You give it a window, and you give it the window you want to be its new owner. I start by asserting that the two windows you give me are top-level windows because, as we noted, ownership is a relationship among top-level windows. And then you use setWindowLongPointer to change the hwind parent, even though it's the owner. This, again, going back to the Windows 1.0 days when parents and owners were all very confusingly misnamed. And this is how you change a window owner. This is a sort of bag of tricks type of thing that you often don't find. It's really not well known. I'm trying to get it more well known. Here you go. The pitfalls of ownership, of course, if you have multiple visible top-level windows on a single thread, this is a problem because you have essentially two different chains of user UI sharing the same stack. If the user dismisses these top-level windows in the wrong order, you can run into trouble when one of them has, for example, put up some modal UI, and then you dismiss the other one, or you get both of them to display modal UI and dismiss them in the wrong order. When I tell people don't have multiple top-level unknown visible top-level unknown windows in a single thread, they try to solve this problem by just grabbing any old window and say, well, see, I gave it an owner. It's not a top-level unknown window. The problem, of course, is that you just grabbed some random window, and it's probably not expecting you to do this sort of thing to it. The solution here is to make sure that any functions that display user interface, that there's a window handle that you pass through to make sure that there is somebody who will be responsible for hosting any temporary UI that the function needs to display. And the last danger point, which leads into the final topic for today, is cross-thread ownership. If you have one window owning another window, and they belong to different threads, you've created thread synchronization. So what is thread synchronization? Well, let's go back to the 16-bit days where everything was synchronous. In the 16-bit days, input was globally serialized. Input came in, there was one input queue. Applications came in, took input off the input queue once they were done processing their own messages. There was one shared keyboard state. If the shift key was down, it was down, end of story. There's only one mouse state. When mouse buttons go down, they're down. There's only one focus window, one active window, one caret, and so on. And changes to focus are synchronous. If one window has focus and somebody calls set focus, or set focus happens for other reasons, the window manager sends the kill focus message to the old window. And since this is 16-bit Windows, everything is cooperative. The window that received the message does its thing, handles the kill focus message. Control returns to the window manager where it can then tell the new window that it has focus. In the 32-bit world, of course, we try to get away from having multiple threads blocking each other. And so input has now been split per thread. If one application stops processing input, this doesn't prevent other applications from processing input. The keyboard maintains separate states. Every thread has its own virtual keyboard state, whether the shift key is down or not, based on what input that thread has received. Every thread has its own focus window, its own active window, its own caret window, or its own capture, for example. And the key point here is that changes to focus are now asynchronous across threads. If one window on one thread has focus and you call set focus from another thread you call set focus and the destination focus window is on another thread, this window is sent his kill focus message. Meanwhile, the thread receiving input gets its set focus message. If the first window is hung, it doesn't matter. The second window will receive focus and keep going. And the window manager has virtualized the fact that focus, this window thinks it has focus, doesn't really. As soon as it wakes up, I'll let him know. And anything he does, if he even asks who focus is, we'll still say, it's you, don't worry, everything's okay. So as a result, every thread thinks it's the only thread in the system. Now, when this was done, there was also this fantastic function called attach thread input, which is also known as, I would like my threads to hang now. When you call attach thread input, what you're saying is that these two threads, I want them to work the old 16-bit way. I want them to share focus, capture, caret, input. As a result, your fates are now intertwined in the same way that the fates of all applications were intertwined on 16-bit Windows. So for example, let's take a look at a focus change once queues have been attached. A window A on thread A has focus. Somebody calls set focus to a window on thread B. If you have synchronized these two threads via attach thread input, the change of focus is now done the 16-bit way, which means that the window B doesn't get focus until thread A has received and processed its kill focus message. If thread A happens to be hung, then thread B also hangs, because thread B can't get input until thread A has relinquished it. Similarly, if these two threads have had their input synchronized, then if the user clicks on window A, clicks on window B, this generates input messages, a click message destined for window A, and another click message destined for window B. Window B is on a thread that's doing fine. It calls get message. it wants to process that click message, but the window manager says, not yet. You and thread A are sharing an input queue, and the top message in that input queue is a message for thread A. So when thread B calls get message, it does not receive input, even though there is input waiting for it. It sees the message and says, I can't process my input until A processes its input first, because you have synchronized the input queues. If thread A is hung, this means thread B never receives its input. Well, this is obviously a very sad state of affairs. You have two threads, one of them goes bad, and the other one just goes bad just for hanging out in the wrong crowd. But I'm not so crazy as to call attached thread input, so I don't have to worry about this. Okay, I'm going to come back to that. The problem is that this thread attachment happens behind your back. If you have two windows on different threads, and you establish an owner-owned relationship between them, or if you establish a parent-child relationship between them, the window manager automatically attaches your input queues. And the reason for this is so that way the user, when the user is interacting with this window, that the input comes through in a consistent manner. That if the user clicks, types, all inside what looks like one window, that the result on the screen should be click, type, click, type. If the input queues were not synchronized, you would see things like click, type, click, type, and you end up with a very confusing situation where the two threads are processing input simultaneously, not coordinated, and input events end up coming through in what appears to be a random order. The last point is that journal hooks are the wild card. If there's a journal hook installed in the system, all threads throughout the entire system have synchronized input. This is why journal hooks are a very scary thing. Journal hooks are typically used for automation, computer-based training sometimes, macro recording. And the input is synchronized so that way these types of scenarios can take the input, inject it into programs, and have the programs react in a consistent manner. This is great for the macro recorder, but it creates problems for you. So how do you deal with input synchronization? Well, so on the left-hand side, an example of something that I see quite a bit. We have a main window. It's about to do some work. It says, ooh, this is going to take a long time. I'm going to kick up a background thread and have it put up a little progress dialog. So that way the user doesn't get all upset. And meanwhile, I'll do my work on the main thread. And I'll tell the background thread how I'm doing, so it can update and look pretty, maybe have a cancel button that it sets a flag that I check every so often. And then once everything's done, I'll tell that progress window, okay, go away, everything's fine, and the main thread goes back to normal. But since these two windows belong to different threads, the input queues are going to be attached. And as a result, this doesn't actually get you anything. If the progress window comes up, the user, instead of interacting with the progress window, starts messing with the main window for some reason. This puts input into the shared input queue destined for window A. Window B, the progress dialog, therefore can't process any input until the main window, which is busy doing work, not even listening to messages, processes them. The user, therefore, mistakenly clicks on your main window for some reason, and then realizes, oh, I'm sorry, there was a progress dialog up. Let me hit cancel. But you won't see that cancel message because there's still the input that the user mistakenly generated waiting in the input queue that is waiting to be processed by your main thread. The solution, therefore, is to avoid this thread synchronization problem, or this input synchronization problem, by putting the progress window on your main thread. So instead of creating a synchronized input situation, you keep all the UI on one thread. The main window creates its progress dialog and then has the background thread actually do the work. As a result, the input, if the user accidentally interacts with the main window, or if the user accidentally interacts with the main window, that thread is still running, can process the input. The user can then click the cancel button on the progress window. And since that thread, again, is still processing input, the cancel actually succeeds. Now, I'm going to go back to this diagram that I skipped. This is for those people know the really scary details of input messages, I'm going to go rather quickly because I'm running over. Input arrives in the raw input thread. The raw input thread very quickly determines which input queue is responsible for this input. It does very cursory hit testing, looks at focus windows, active windows, puts the input into the appropriate input queue. Meanwhile, these threads run. They call get message or peak message. They go looking in their message queue. They pull out the messages out of their message queue. Once you've drained your message queue, then we look at your input queue. The message comes out of the input queue, and it might be that the initial guess that the raw input thread made was wrong. So for example, in this case, thread A, if the raw input queue mistakenly decided that this was a message for thread A, or a message for thread, mistakenly thought this was a message destined for a window on thread A. Thread A is going to come in, it calls get message, looks at the input queue, and then realizes, oh, I'm sorry, this is a regional window, I need to do some more careful hit testing. Oh, you hit a hole in window A, it really should go to input queue B. The message then moves to input queue B and waits for thread B to come and pick it up. In the case of in the bottom half is the case of synchronized input, where there's one input queue for C and D. And as I described before, thread C and D both share that input queue, and the input messages have to be pulled out in the order they were placed into it. All right, and final notes. Evaluation forms are all online this year, so fill them out. Let me know how boring I was. I will be in the Fundamentals Track Lounge for the remainder of the day today, and I will be at Ask the Experts this evening at the Windows System Internals table. And if you have a question, feel free to walk up to one of the microphones and let me have it. Yes?
You mentioned that on a regional window, if you click a hole, it might end up on the wrong queue.
Right.
Does that introduce some input synchronization problems between multiple threads?
There is. It does mean that the input message ended up in the wrong place for a little while. I'm not sure whether this actually creates a problem or whether the system is smart enough to. So the answer is I don't know.
Okay.
You can stop by and we can talk about it later, and I can go back and do some more research on this.
Okay, thanks.
Okay, I'm sorry. Is there? Yes, in the middle.
Yeah, I'm somewhat embarrassed to admit this, but I actually have links to your blog entries and comments in my code. So.
Oh,
that's pretty funny.
Well,
but,
well, then I guess you better hope that my blog stays up.
Yeah, well, you know, job security.
Okay. Well, now I know where the hits are coming from.
I have a question about, you know, a common problem is your app is in the background and something happens, you need to notify the user. You put up a dialog. Windows makes it very hard to force a window to the foreground, as you know. And so you get like the little blinking taskbar icon, which isn't always good enough to notify users that something's going on. So do you have any suggestions on alternate ways to do that UI? Or, you know, what are your feelings on being able to force windows to the foreground? Is that one of the things that's played nice with others?
Right. As a general rule, the window manager tries to prevent application from forcing foreground because that's sort of a force for evil. Well, it's a force for both good and evil. And we've increasingly discovered that if you give someone the power for both good and evil, a good chunk of them will use it for evil. The recommended solution for this type of thing is asynchronous notifications, because as I've written, and some of you may have read, users ignore dialog boxes that they're not expecting to see. So if the user is minding their own business, doing blah, 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 and then boom, some dialog box shows up that they weren't expecting, they're just going to say, yeah, they're just going to hit the X and go back to what they're doing. So your wonderful dialog box didn't help them much anyway. I believe the guidance on this is to use a notification balloon. This is to tell users that there's something that happened that they should take a look at eventually. But the goal of that is to try not to interfere with what the user is doing right now.
Right. Okay. Thanks.
Okay. Yes, in the middle.
I'm curious what happens if you have different DPI settings on a PC which is using, say, virtual desktop to come into another one. So the PC I'm sitting in front of is at 144 DPI, and I remote desktop into one that's at 96. Is there some fix-up that happens, or is it a pixel per pixel?
It is my
translation?
understanding that remote desktop transfers bitmaps across. It doesn't try to do any DPI adjustment along the way. That is my understanding. I could be wrong. I'm sorry.
So if my screen resolution in pixels matches, then I'll
Then
see.
everything looks great. And if, for example, you're on a 96 DPI machine and you use terminal services to connect to a 120 DPI machine, the arithmetic is still going to happen on the remote machine. It's going to decide that the font is 21 pixels tall, and then a 21 pixel tall font is going to show up on the machine that you're connecting from.
Great. Thank you.
Okay, thank you. Sir, in the middle?
Still in the middle. All my MFC apps, if you have a message box showing and then you try to exit the app, it crashes. Is
So
this
all-
big?
MFC apps?
Yeah, is this
Okay.
because those input queues are tied or something?
It depends on how that message box was displayed. I'm not entirely. We'll have to. You can stop by the fundamentals lounge and we can try to dig into this a bit more. This is without doing some looking around. I'm not quite sure what's going on.
All right, thank you.
I'm sorry. All right. Well, thanks for coming. Oh, wait, there's one more. Did we have a question in the middle?
I have a Windows form and a MFC application. Well, basically, I have an MFC window inside a Windows form window. And what Windows Forms does when we show and hide the window is actually destroys the MFC window. Is there a way that I can prevent it? I've been playing with it on the owner windows and parent windows, and I can't seem to figure it out.
Yeah.
The trick I'm playing right now is basically changing the parent window of the MFC application to the main application window, and then hiding the MDI window,
Right.
and then putting it back when I show it. But is there a way? It causes a bunch of flickering, but I'm not sure what to do with that.
Yeah, I'm not sure either. I think if you can stop by the fundamentals lounge and we can both walk on over to the presentation area, and then the Windows Forms people and I, perhaps together, we can come up with an answer.
Okay, cool.
Okay.
Thank you.
Sorry. Yes.
In the slides that you showed in Vista, it's an opt-in to support the high DPI. Are you not penalizing the application that did their job for Windows XP and below?
Yes. It's true that applications that did the right thing are going to suffer effectively a penalty for they went through all this work and they still look awful. The decisions and the technology on the DPI scaling is still not final. I will bring this point back with me, and I suspect, although this is not a promise, but I'm guessing that there will be some sort of way for end users to mark an application so that with the compatibility engine will say, we've tested this app, it looks good at high DPI on its own, it doesn't need help. But that's just my guess as to where things may go in that direction.
Thank you.
Okay, thank you. All right, well, I'll let you all go to lunch, I guess, or the next session. And thanks for coming.